All right. So some of what I had to review with you was changes to the schedule and outline and so forth. Okay, so 2.1 we're keeping. 2.2, first I'm adding one more problem, 19 to 27. It was originally 25. Include 27. But after that, only at the odds. So notice in 2.2, there's a mixture of evens and odds. Because of what happened last week, I'm going to change it to only the odds. Okay, 2.3, skip problem 1, so it's 3 to 31 odd. And we're skipping 2.4 altogether. We're not going to do it at all. Okay, and you will not be severely put back or handicapped by not having 2.4. It's a nice topic, but in considering what happened last week and everything else that we're putting up with already, I decided to throw it out. Okay, so schedule-wise, let's see. So we are here, right? So this was last week. I theoretically gave you 2.1 and 2.2. I'll rush through a lot of it already. So 2.3, maybe today and tomorrow. And so skip 2.4 completely. And if I can do that, then we're on to our regular schedule 2.5. Okay. Of course, you were not marked absent for any of last week. So don't worry about attendance last week. Obviously, there wasn't any. And as I mentioned, Friday, I was supposed to give you a quiz. My spreadsheet already has a quiz, so the only fair way for me to do it was everybody automatically got 5 points. So you got 5 points for doing nothing on Friday, okay? So good deal with that. There was a quiz 3, and you automatically got 5 points, okay? All right, so now I'm gonna go back and show you some stuff from where we were. Now, I don't recall if I actually gave you pictures of all the important pages. So I'll run through some of that right now again. So 2.1, page 82. So here's that, and you can catch that from the video, hopefully. So that goes up to 6. So here's a little bit more. A little bit more. All right, so as I mentioned, tried to mention, 2.1, a lot of the problems were just computing slopes. Okay, so for instance, for number 1, what I tried to mention to you, both on the video and the attachment, was, for instance, 15 comma 250, we have that. And they say the slope of the secant line, so you got a fixed point, 15, 250, and then t equals 5, 10, 20, whatever. So you have 15 comma 250 and 5 comma 694. So now you're just doing the formula for the slope, right? So you have these two and do y2 minus y1 divided by x2 minus x1. Same thing for all the others. Let's say 30, you're using 15 comma 250 and 30, 0, and you're finding y2 minus y1 divided by s2 minus x1. Estimate the slope of the tangent line by averaging the slopes of 2 secant lines. Okay, the best approximation will be the close by ones. So how about get the answer you got from taking these 2 points, you get a slope, right, of a secant line. And then these 2 points, they're closest, and just average those two. Okay, so remember, we're kind of going back to this picture. This was even before the test, right? So if you take 2 points that are very close, the slope of the secant will be a much better approximation of the slope of the tangent than if you pick 2 points that are far away, right? So notice the blue line and the red line are worse here and here because P and Q are far apart. But in these 2 instances where P and Q are close, one coming from the right side, one coming from the left, then notice the the red and the blue are very close. The secant line and the tangent lines are very close. Okay, and then what I tried to show you, not very well, but a little bit on the video, and I'll do that a little bit better here. Okay, so for problem number 1, I plotted these points. Just take all these points and plotted them. And I should have emailed you that attachment also. You should have gotten that as the attachment. Okay, so I connected all these. I drew the tangent to the curve, the green line. And I picked 15 comma 250 and 0 comma 700. Now, your tangent line may not be exactly the same as mine. That's okay. And so the M tangent, M tan, came out to be negative 30 gallons per minute. Okay, so right at this particular moment in time, 15, 250, we're losing about 30 gallons a minute. It changes as time goes by. All right, for number 3, it was pretty much the same thing. It's a lot of y2 minus y1 divided by x2 minus x1. Okay, so your fixed point was 2, negative 1. That was like the fixed point, and the moving point Q, going back to that picture, right, is all of these. So 1.5, 1.9, 1.99, 1.999. We're getting very close to P coming from the left side, and 2.5, 2.1, 2.01, 2.001. We're getting very close coming from the right side. So that's an actual application of this picture here, right? So we're getting real close coming from the left, and then we're getting real close coming from the right. All right, so I chose just 2 of them. So for part A, number 4, it was 1.999. If you plug it in, you get 1.999, negative 1.001001. Throw it into the formula for slope. Comes out to be 1.001 repeating, 1.001, and so on. Then part A, I did number 8, 2.001. If you plug in 2.001, you get negative 0.999000 repeating. Bar means repeating. Throw it in the formula for slope. Comes out to be 0.999000 repeating. Okay, and of course, these 2 would be the best approximations. After all, these 2 are the closest to the number 2, right? So those secant lines would be very close to the tangent line. Okay, so on one side, you got 1.001, the other was 0.999. So a very good approximation for the slope of the tangent line would be 1. And then what's the equation of the tangent line? Y minus y1 equals m times x minus x1. Y minus a negative 1 equals 1 times x minus 2. Okay, and we'll just leave it like that in general. Okay, mention quickly again. So y minus y1 equals m times x minus x1. Right? This is sometimes called the point slope form. We're going to be using this over and over and over in this course. Okay, now, some of you, especially in the last test, avoided using the point slope form by switching over to y equals mx plus b, and you can do that, but you're not going to be able to do that here. You need to know the point slope form. Many, many times in our class, I'll ask you to leave the answer in point slope form. So you have to use this form, not go back to y equals mx plus b and plug in. All right, so you need to know this. If you never heard of it, which shouldn't be the case, you put it on your cheat sheet for exams. Okay. All right, and then let's see, number 7, again, which was somewhat similar. I plotted all the points, and the tangent line is the green. I just graphed what was in red from the given points, and the slope of the tangent. Right, so y2 minus y1 divided by x2 minus x1. Okay, that looks like it was about 1.8, 0. How did I get that? I just drew a tangent line. Okay, you can tell I'm just guesstimating. So if yours isn't exactly the same, that's fine. All right, so that comes out to be 38.75 feet per second. All right, so that's all I wanted to say about section 1. Okay, now section 2, and I know I rushed through a lot of it. Okay, so this new calculus concept of the limit of a function. So on page 83, limit as x approaches a of f of x equals L. Limit of f of x as x approaches a. Okay, so we're not really plugging in a. We're plugging in numbers that are very, very close to a. And the illustration here, okay, so the language limit as x approaches 2 of x squared minus x plus 2 equals 4. Now, we're not really asking what happens when you plug in 2. It is true when you plug in 2, you get 4. That's easy to verify. Plug in 2 here, 4 minus 2 plus 2 equals 4. But that's not what this says. This says if you plug in numbers that are very, very, very close to 2, okay, you get numbers that are close to 4. So they made a table. Notice they approach 2. These are numbers approaching 2 from the left, right? You're coming from the left. 1, 1.5, 1.8, 1.9, 1.99, 1.999. We're getting real, real close to 2 coming from the left side. Here we're getting very close to 2 from the right side. Okay, so starting at 3, and then we're moving in 2.5, 2.1, 2.01, 2.001. We're getting really, really close to 2 coming from the right side. So if we look at the progression of the numbers, okay, so here we're going to 3.997, here 4.003. So it looks like we're approaching 4. So the limit is 4. Yes, in this particular case, it is true when you plug in 2, you do get 4, but that's not what this says. This says when you plug in numbers that are really close to 2, the y values get really, really close to 4. Okay, so that's what that is all about. Then on the top of 84, I tried to show you 3 instances. Here are 3 pictures where the limit as x approaches a of f of x equals L in all 3 cases. So here, when x is a, y is L, that happens to be on the graph, but we're not interested in that. We're saying when x gets real close to a, either from the left or the right, the y values are close to L. Picture B, they have this graph, and then there's an open circle here, and then they put a dot down here, but they continue on here. So nevertheless, they're still going to say the limit as x approaches a of f of x is equal to L, because when we get real close to a, coming from either the left or the right, the function values are close to L. Even though right smack dab at a, directly at a, we're down here, but we don't care about what happens right at a. We care about what happens when we're close to a. And then picture C, f of a is not even defined. Okay, so I say, what is f of a? Notice there's a hole here. F of a is not defined, and yet we're saying the limit still exists. The limit as x approaches a coming from the left or from the right, the y values are close to L. Okay, and here's an illustration here. Limit x as x approaches 1 of this expression does exist. You can't plug in 1. Notice when you plug in 1, you get 0 on the bottom. But we're saying the limit exists. So what did they do? They made a table. They got closer to 1 from the left. 0.5, 0.9, 0.99, 0.9999, right? And they approached 1 coming from the right also. 1.5, 1.1, 1.01, 1.001, 1.001, right? So if you notice what happens to the y values, they get close to 0.50025, 0.4999. Okay, so both of these seem to approach 0.5 or a half. So we're going to say that the limit of the function as x approaches 1 is a half, even though f of 1 itself does not exist. And I'm trying to show you that from the picture here. Okay, so from the picture, it looks like the limit exists, even though right smack dab at 1, we're not allowed to plug in 1, right? Okay, so that is that. Then we had, here's a limit, which is nice. You don't have to memorize it, or we're going to use this a little bit later on, so you can put it on your cheat sheet. Limit as x approaches 0, sine of x over x. Now, frankly, if we were meeting face-to-face, I'd make you guys memorize it. Since we're under COVID, we're supposed to make things easier on you, so you don't have to memorize it, okay? But limit as x approaches 0, sine x over x. You cannot plug in 0. But we're saying the limit exists because even though you cannot plug in 0, we're saying what happens when you plug in numbers that are real close to 0. Okay. Now this happens to be an even function, which means when you plug in negative x, you get the same thing as x. So notice the table, plus or minus 1, plus or minus 0.5, 0.1, 0.01, 0.001. Okay. So 0.84, 0.95, 0.99, 0.999, 0.99999. We're getting really, really close to 1. So our guess is that the limit as x approaches 0 of the sine of x over x is equal to 1. And here's the graph. I don't know if you can see it, but there's an open circle right there. So coming from the left or from the right, as we get really, really, really close to 0, the y values are close to 1, but right smack dab at 0, the function is not defined. You know it's not because you can't plug in 0. But if you plug in numbers that are real close to 0, we're getting really, really close to 1, as you can see. So this limit is equal to 1. Okay, then we have one-sided limits. If you see a minus sign here, it means you're only coming from the left. If you see a plus sign there, it means you're only coming from the right. So if you don't see a symbol there, it's two-sided. You're coming from both the left and the right side. Okay? Minus sign, so approaching 0 only from the left. If I'm only coming from the left for this particular function, the y values are at 0. So I would say the limit is 0. But limit as t approaches 0 with a plus coming only from the right, only coming from this side, then I would say the y values are up at 1. Right? So in this particular case, the two-sided limit does not exist because the limit from the left does not match the limit from the right. So the minus sign means you're only coming from the left. The plus sign means you're coming only from the right. And no symbol at all means it's two-sided. It's a two-sided limit. All right. And your limits can be infinity. Find this limit. Limit as x approaches 0 of 1 over x squared. Again, this is an even function, so let's approach 0. Plus or minus 1, plus or minus 0.5, plus or minus 0.1. Right, so what's happening? So the numbers are blowing up. Right, so we would say that the limit is infinity. Limit as x approaches 0 of 1 over x squared is infinity. And you can see from the graph, right? The graph shoots up like crazy. If you plug in smaller and smaller numbers, the y values get bigger and bigger and bigger. So yeah, your answer is allowed to be infinity. Okay. And yeah, so I'm going to show you some of this. So I tried to show you some of these already. So again, change the assignment. Anything that's even, forget about it. I am going to include 27, although I sort of went over it already. Okay, now I haven't tackled which one? Number 9 yet. Okay, so let me do number 9. Unfortunately, number 9, the questions are here at the bottom, but the picture is here. Okay, so if you don't mind, I'm just going to read it off here. Oh yeah, maybe I should show you this again. So in case you don't have the book. So here's the homework 2.2 up to part of 7. So there's more of 7 and 8 and then 9. Okay, so here are the questions for 9. I'm just going to show you the picture later. So here's the next page. Okay, up to 19-ish. More. And more. All right. And next page, some more. I believe we had to stop at 41, so there's that. Okay, and 2.3, I might as well give you what you need. So here are limit laws. So top of 95, 2.3, limit laws, that. Okay, I'll let you look at these, although most of these are somewhat intuitive. Page 96, 6, 7, 8, 9, and 10. Limit laws. And the root law number 11 on page 97. At the bottom, direct substitution property. It'll be straightforward when I do some problems with it. And let's see. Show you the greatest integer function, page 101. Here's the graph of the greatest integer function. You write it like this. It's like 2 brackets together. Okay, squeeze theorem. I'm actually not going to talk about it in this section. I'll come back to it later, but make a note, there's something called a squeeze theorem. If there's a function that's squeezed between 2, they'll all have the same limit. But I just thought I'd mention that right now. And start showing you some of this stuff. So 2.3, what page are we? 102. So if those of you who don't have the book and don't plan on getting it, there's that. A little bit more. Next page. Okay, that takes you up to about 47, so a little bit more. And some more. All right. And then problem 53, I believe you had to do. It's the greatest integer function one. All right, and we're skipping 2.4 altogether, so never mind about that. All right, so let me go back, and I did not show you in the video I made last week, number 9. So let's look at this picture for number 9. Okay, and I'll just read it because it's too hard for me to go back and forth. I'll just read them for number 9. limit as x approaches -7. So the limit as x approaches -7, it's two-sided, so that they both drop down to -infinity. Okay, so 9a, put -infinity. B, limit as x approaches -3. So as x approaches -3 on both sides, so it shoots up to positive infinity. Okay, so 9b is positive infinity. 9c, limit as x approaches 0. So we approach 0 on both sides. Again, it's positive infinity. So 9c is positive infinity. 9d, limit as x approaches 6 from the left. Okay, I should show you this one. I don't know if you can see it, but there's a minus sign there. Limit as x approaches 6, only coming from the left side. So only coming from the left side, the y values drop to -infinity. So the answer to D as a dog is -infinity. E says limit as x approaches 6 coming from the right side. So if I come only from the right side, it shoots up to positive infinity. So the answer to E is positive infinity. So the question doesn't ask for it, but what would the two-sided limit be? The two-sided limit does not exist. You may abbreviate DNE, does not exist for me, for does not exist, because you don't get the same limit from the left as from the right. Okay, then F, the equation of the vertical asymptotes. So it's always going to be x equals something for the vertical asymptotes. So F, vertical asymptotes, x equals -7, x equals -3, x equals 0, and x equals 6. So those are the vertical asymptotes. They all start with x equals, you might recall, for vertical lines. So x equals -7, x equals -3, x equals 0, x equals 6. All right, and I'm willing to go back and show you number 5, even though I went over it on the video a little bit. Okay, so here's the picture, and here's what we have. Okay, so A, I know it's hard to read. Limit as x approaches 1. So as x approaches 1, that's both sides because there's no plus or minus there. So if I approach 1 either from the left or from the right, the y values are at 2. So the answer to 5A is 2. B, there's a minus sign there next to the 3. So limit as x approaches 3 coming only from the left. So if I come only from the left side, the y values are down here, which is 1. So the answer to B is 1. C says the limit as x approaches 3 coming from the right. So if I approach x equals 3 coming only from the right side, the y values are here, and where's here? That's 4. Okay, so D, there's no symbol there, so it's two-sided. Limit as x approaches 3 coming from the left and the right. Well, it's not the same thing, so letter D does not exist. D and E is the answer to that. And then E, F of 3. So right smack dab at 3, right at 3, not a little bit to the left, not a little bit to the right, exactly at 3, there's a dot right here. So F of 3 would be 3. Okay, so that's it for that one. All right, and let's see, the next thing I wanted to show you from 2.2 was something like, I'll show you 11. 11, sketch the graph and determine the values of A for which the limit does not exist. Okay, so here's the piecewise defined function. I'll just run through it very quickly. You should know how to graph these, and I went over it in the video, sort of. Okay, so 1 plus x looks like that. It's a line. X squared, we know, looks like that. 2 minus x looks like that. So the two-sided limit, x approaches a of f of x, exists for all real numbers except for -1. So at -1, right, if you approach from the left, the y values are close to 0. If I approach from the right, the y values are up at 1. But for every other real number, it's smooth, it's continuous. As you can see, there's a two-sided limit that will exist. Or you can say for the set of real numbers minus a set consisting of -1. All right, I wanted to go back and do 15 and 17 for you now. So sketch the graph of a function that satisfies these conditions. Okay, so let me see if I can show these both to you at the same time. Sort of. Okay, so the limit as x approaches 0 from the left of the function is -1. So as I approach 0 coming from the left side, I'm down at -1. The limit as x approaches 0 from the right, there's a plus sign there, I'm not sure you can see it. The limit as x approaches 0 from the right of the function is 2. So I get real close to x equals 0 coming from the right, you get 2. By the way, this little squiggle here, it doesn't really matter. You could have it go straight there or squiggle and come to here. The main thing is that we approach here and likewise here. I mean, you can jump up if you want. And then f of 0 equals 1. So right smack dab at 0, right at 0, there's a dot at 1. So that's what the graph would look like. Okay, then I'll show you 17 also. I've been showing you this before. So 17, yeah. So here's 17. Limit as x approaches 3 coming from the right side of f of x is equal to 4. So as I approach 3, x equals 3 coming from the right side, the y values are up near 4. Open circle. The limit as x approaches 3 coming from the left is 2. So the function approaches 3 from the left side, we're right here. Limit as x approaches -2. Now, you can't see a plus or a minus there. That means it's two-sided. Coming from the left and from the right, the y values are near 2. So coming from the left and also the right, the y values are near 2. But f of 3 equals 3, and f of -2 equals 1. These are just dots, folks. When they give you that, this just means plot 3, 3. Okay, there's 3, 3. Plot -2, 1. There's -2, 1. Okay. That's all I have to do for those. All right, so I wanted to show you those. And then you have a lot of problems where you're just punching into your calculator, like 19, like 21. Okay, so for instance, notice here, limit as x approaches 3. Now, you cannot plug in 3, right? When you plug in 3, you get a 0 on the bottom. But you can plug in numbers close to 3 from both sides. So your job is to just plug into your calculator, 3.1, 3.05, blah, 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 up to 3.0001. And likewise, 2.9, 2.95, 2.999, right? And so on. And see if you approach any number. The number that you approach is considered the limit, two-sided limit. Okay, so let me show you what I did for 23 and 27. So I tried to give that to you before. Okay, so limit as x approaches 4, and all the other problems from that section are kind of like that, of ln x minus ln 4 over x minus 4, okay? I claim this limit exists. The limit does exist, even though you cannot plug in 4. How come you cannot plug in 4? You get a 0 on the bottom. But that's not what this symbol means. This symbol means x is not equal to 4, but it's very, very close to 4, okay? On both sides. So what you want to do is approach 4 from the left, 3.9, 3.99, 3.999, and approach 4 coming from the right, 4.1, 4.01, 4.001. Now, you actually have an advantage for 19 and 21. That's one of the reasons why I didn't show it to you, because they gave you the numbers to plug in. You know what to plug in, okay? For problem 23, though, and 25 and 27, they didn't tell you what numbers to plug in, so you make up your own. Right? So I just said, okay, well, I'm approaching 4. So here I'm approaching 4 from the left. I'm approaching 4 from the right. Okay, you can plug into a calculator as well as I can or better, but just punch it in. These are the things I got. Right? So 0.253, 0.250, 0.25003, 0.2469, 0.2497, 0.24997. Okay, are we getting close to any particular number? Yes, it looks like we're getting close to 0.25 or 1/4, a quarter. So my conclusion is that the limit as x approaches 4 of ln x minus ln 4 divided by x minus 4 appears to be 0.25 or 1/4. Okay. Now actually, later on in this course, we're learning how to figure this out analytically. There's a way to do this analytically without just keep plugging in and making a table. There's a much better way of doing it, actually. Okay. Okay, 27, which I said to include, but no big deal. You're not really doing it. I'm doing it because I already did it. Okay. It was x approaches 0, and there was a plus sign there, which means you're only coming from the right side. So I don't have to plug in numbers that are coming from the left, like negatives. I just did 0.1, 0.01, 0.001. So 0.1, that means 0.1 raised to the 0.1 power, 0.01 raised to the 0.01, 0.001 raised to the 0.001. Okay? This is what I got, 0.9931. Okay, so it looks like in the limit we're approaching 1. And that does happen to be the case if you plug in numbers that are even closer. I know, I can do this for fun, I think. Let me say a 0.0001. Okay, so just for fun, let me do 0.001 raised to the 0.001. 0.993 got even better, right? 0.0001 raised to the 0.0001. 0.9990, so it gets closer and closer to 1, as you can see. So the approximation gets better and better. Okay, and then one infinite limit I want to show you was 31. Okay, limit as x approaches 5 coming from the right, that's what the plus means. If it said a minus, I would do 4.9, 4.99, 4.999, x plus 1 over x minus 5. Okay. Again, we're not really plugging in 5. We're plugging numbers that are close to 5, approaching from the right. So 5.1, 5.01, 5.001. Plug them in. 61, 601, 6001. Well, the numbers are just getting bigger and bigger and bigger. So I'm going to say limit as x approaches 5 from the right of x plus 1 over x minus 5 is infinity. So I guess the answer is infinity for that one. Okay. So there you go with that. All right, so now I'm going to introduce some of 2.3 in the short time that we have left over. Okay. All of these laws, they're good, laws. The limit of a sum, the language is the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. What does that mean? If you have the limit of something plus something, you can take the limit of first plus the limit of the second. Same thing for a subtraction. Same thing for a multiplication. Same thing for a division. The formal language is the limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits, provided you're not dividing by 0. The only one that's a little bit different, but it's still intuitive, the limit of a constant times a function, you can factor that constant out. C stands for constant. It's a constant times the limit of the function. The limit of a constant times a function is the constant times the limit of the function. Okay. Yeah. I would say don't really, worry too much about these. We're going to end up doing these. So even though I just say here they are, they're all true, we're just going to end up doing them. Okay. As we do them, you see they're rather intuitive. Same with these here. Okay, but let me just go ahead and get started with limits. Okay, the direct substitution property, that says if you can just plug it in, do it. Okay, most of the problems aren't going to be that easy. Okay, well, how about I just plug it in? If you can plug it in and get a real number, do it. But for most of the problems, you're not going to be able to plug it in because most of the time you're dividing by 0. So we got to do some algebra. Okay, of course, right now you're probably saying, what are you talking about? So let me go straight to some examples of this. Okay, again, skip problem 1. I'm throwing out number 1. So starting with number 3, evaluate the limits. And here's what I mean. If you can plug it in, just do so. So 2.3, again, skip the date. Date's irrelevant. Limit as x approaches 3 of 5x cubed minus 3x squared plus x minus 6. Okay, plug it in. 5 times 3 cubed minus 3 times 3 squared plus 3 minus 6, blah, 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 105. Now, what are you missing by not doing all the formality? What they want you to do is break this up as the limit of that minus the limit of that plus the limit of that minus the limit of that. It's fairly straightforward. It's obvious. Okay, that's what they mean by the limit of a sum is the sum of the limits. Limit of a difference is the difference of the limits. And what they would want you to do is to break this up. Like suppose it was just limit as x approaches 3 of 5x cubed. You can factor the 5 out. Take the 5 out, limit x approaches 3 of x cubed. That's what I mean. It's sort of intuitive. Just plug it in. Okay? So if you can plug it in, just do so. They don't give you that many of those problems because that's too easy. It's just algebra 1. Okay? So what makes the problem harder is 11, 17, 21, 23, where you cannot just directly substitute. Okay? Now, if you can just directly substitute, go ahead. It's pretty easy. I think 5 is like that. 7 is like that. I'm not sure if you can see it right now, but 7, it looks complicated. Just plug it in. So what makes it harder is stuff like this. 11. Limit as x approaches 5 of x squared minus 6x plus 5 over x minus 5. Okay? You cannot plug in 5. So how do we find the limit? Okay. One way to do it, which we now know is not very fun, is, just get out your calculator and do what? 4.9, 4.99, 4.999, and 5.1, 5.01, 5.001. You don't feel like doing that. I don't feel like doing that. It's a lot of work, right? If we can do some algebra, it's a lot easier. In this case, we can do some algebra pretty easily. The top factors into x minus 5, x minus 1, right? And lo and behold, cancel this out. That's allowed as long as x is not equal to 5 and x is not equal to 5. It is close to 5, but not equal to 5, right? So now you just have to limit as x approaches 5 of x minus 1, and that's easy. Now you can directly substitute 5 minus 1 equals 4, right? And you can see that's way better than, 4.9, 4.99, 4.999, plug it all in. 5.1, 5.01, 5.001, plug it in. Okay, if you can do some algebra, it's way better, as you can see. Okay? It's actually considered more accurate. All right, so the last problems I will show you for today, what time is it? Less than 10 minutes. Okay, you have to do some algebra trick to simplify. Right, so 17. Again, notice for 17, you can't plug in, right? So why don't I just plug in? Like this one, all I did was plug in. Yeah, they're not going to give you that many of those problems. If you just plug in, it's really just algebra 1. Okay, so what do I do here? Now, again, even though you cannot plug in 0, I claim that this limit exists because this statement means you're not really plugging in 0. You're plugging numbers that are very, very close to 0, which we're not really going to do. We're not going to plug in 0.1, 0.01, 0.001, and negative 0.1, negative 0.01, negative 0.001, because that takes too long. Much faster is algebra. Okay, so I clean this up. If I square this, I get 25 minus 10h plus h squared, right? It's a squared plus 2ab plus b squared comes out to be this, minus 25 all over h. So the square of negative 5 plus h is all this stuff. And then minus the 25. Now a little bit of algebra. 25 cancels 25. And then these two are the only ones left. And notice I can factor out an h. Right? So take out the h parentheses, negative 10 plus h. And what do you know? I can cancel that h with that h, right? So cancel that out. Limit h approaches 0 of negative 10 plus h. Now you can directly substitute. So just plug in 0 and you get negative 10. And by the way, symbols that you're supposed to use, and this is proper, and I'm going to check for this when you turn in your quizzes and your exams. I'm going to check for this. You're always supposed to write limit, or lim for short, lim h approaches 0, lim h approaches 0. You're supposed to write it all the way through until you're ready to plug in the 0 right there. Okay? So don't be cheap and just leave off the lim and say, okay, I know it's there. No, in fact, mathematically, it's not equivalent. That is not equivalent to this unless you put limit h approaches 0. And this is not equivalent to this unless you put limit h approaches 0. So if you don't put limit h approaches 0, I'm allowed to mark it wrong. Okay, I mean, I'll give you partial credit for doing everything here right, but you're supposed to keep writing lim, 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 lim until you're ready to plug in. Then when you finally plug in, then you can take off the lim. In fact, I'll be stronger. Your final answer should not write the lim. You should not put lim in your answer. Your final answer is just a real number. Or later on, some expression like x squared or something like that. Okay, so let me see if I can show you a couple more. Number 21. The original problem, limit as h approaches 0 of radical 9 plus h minus 3 all over h. Notice again, you cannot plug in 0. So how do I do the algebra here? The trick here is to multiply by the so-called conjugate of the numerator. Okay. So the numerator, these are called conjugates. It's sort of like we're rationalizing the numerator. In algebra, you rationalize the denominator. Okay. If you have radical 9 plus h minus 3, you multiply top and bottom by radical 9 plus h plus 3. Right? So notice this expression is still 1. Right? Anything divided by itself is 1. If I take any expression multiplied by 1, I'm not changing its value. I get an equivalent expression. But the reason why you do this is because now it looks like a minus b, a plus b. And from algebra, what is a minus b, a plus b? That's just a squared minus b squared. So once again, these two are called conjugates. Radical 9 plus h minus 3, radical 9 plus h plus 3. So by formula, it's a squared minus b squared. So what's radical 9 plus h squared? Oh, it's just 9 plus h. Minus b squared. 3 squared is 9. Okay, and by the way, don't multiply at the bottom. There's a good reason not to multiply at the bottom, as I'll show you just in a moment. Okay, and you have 9 minus 9, which cancels out to be 0. So you only have h on top. Guess what happens with that h? It cancels this h, which you might have missed if you went ahead and multiplied this out. So usually you don't want to multiply out the bottom. Just leave it as h. That h cancels that h, which means you just have a 1 on top. So now you have limit h approaches 0. Again, notice I keep writing limit h approaches 0. Limit h approaches 0, or lim, L-I-M for short. Lim h approaches 0. 1 over radical 9 plus h plus 3. Now you can directly substitute, no problem. So put a 0 right there. 1 over radical 9 plus 0 plus 3. Square root of 9 is 3. 1 over 3 plus 3. Answer is 1/6. All right, so that's how you do this problem. And so if you can do some algebra trick to clean it up, then do so. Now, you might think this is quite lengthy. Yeah, it was kind of lengthy, but this is way, way better than making your table, right? And going 0.1, 0.01, 0.001, plus or minus, punching it all in, right? That's a real bear. Okay, I think I just have enough time to show you 23. Okay, so the original problem, limit as x approaches 3, 1 over x minus 1 over 3 divided by x minus 3. Now you say, why don't I just plug in 3? You cannot plug in 3 because 3 minus 3 is 0. You'll be dividing by 0. So there must be some algebra trick. Okay, so first I'm going to multiply top and bottom by 3x to clean up the denominators here, right? So 3x, 3x. So the bottom, the denominator becomes 3x times x minus 3, right? Don't bother multiplying it out. There's a good reason for that. Okay, so 3x times x minus 3. And look at what happens on top. What's 1 over x times 3x? Well, x cancels out, and you have 3. And what's negative 1/3 times 3x? That 3 cancels that 3, so you have negative x. So you have 3 minus x. And we have this recurring theme that we saw in the first exam even, right? I gave a question like that in the first test, in the first homework. What is 3 minus x divided by x minus 3? That's not 1, that's negative 1. This cancels out to be negative 1. So now I have limit as x approaches 3 of negative 1 over 3x. Now you can directly substitute. So plug in the 3, negative 1 over 3 times 3. Final answer is negative 1/9. And there we go. Okay. All right, so I know I went through a lot of sections 1 and 2 fast, but hopefully you were able to see some of that from the stuff I gave you last week. Okay, all right, so let me see, that's that. Let me check the chat if there's anything. Christian, I see you got that. Well, 2.3, yeah, I'll do more 2.3 tomorrow. And okay. What is this week's quiz going to be on? I'm not sure. I'll tell you Thursday. Let's see. Plug-in numbers. Yeah, I know I won't have time to answer all your questions, but yeah, ask me again tomorrow. So plug in the specific number if you're able to. Well, like number 3. I showed you number 3, right? Plug it in. If not, try to do algebra first. Okay, algebra is way better than plugging the close by numbers. And I think that's all we have here. And yeah, Christian, that means I got you for attendance, so I got you there. All right, so let me see. Anything else from the chat? Sorry about that, folks. I know it seemed like I was going 100 miles an hour, but I tried to pick up some of the stuff from last week also. Okay, and I think that's it for the chat. So sorry, I won't be able to answer all your questions, maybe tomorrow, but we'll pick up from here tomorrow. All right, and again, we're completely throwing out section 2.4. So 2.4 won't be covered on any homework or any quiz or any exam. And you can survive Calc 1 without it. In fact, I've seen some course outlines in some schools that don't even have that topic, so you're still going to be good. All right, so I think that'll do it for today, folks. So we're back for now. So have a good afternoon, and we'll see you all tomorrow. All right, so thanks. Have a good day. Bye, everyone.
Thank you.
Thank you.
Thank you.
Goodbye.
Thank you.